Okay, so here's another question from Morin. We're going to start adding in a few extra forces when we're doing these projectile problems now. So let's think about this. Imagine we're throwing a ball into the wind. So now there is some sort of wind force. And later, much later, we'll get to how to handle projectile motion with drag. For now, let's assume that this wind force is a constant force. Let's say it's blowing to the left. And let's also say that the magnitude of the wind force is just equal to the weight of the ball. So it's a constant force blowing to the left that happens to have the same magnitude force as the downwards force of gravity on the ball. The question is, if I'm standing at the top of a cliff and I throw a projectile directly horizontally, I'm leaving off a lot of the wording in the prompt, and I throw this ball directly horizontally at some speed v0, what should that speed be so that the ball is actually blown back and lands right at the base of the cliff? Okay, so notice that because this force is constant, I can just immediately write down my parametric equations for position without really too much extra thought. Let's recall the general constant acceleration kinematics equations. Okay, these are the equations assuming a constant acceleration, which means a constant force, and that is what we have in this situation. So now let's try to plug in what we know and see if we can get some system of equations involving this time t that we're maybe not interested in to solve for that v0 speed for landing back where we started. So notice that my final x position and my initial x position are both 0. I'm starting and ending along the y-axis. My initial x velocity is the thing I'm trying to find. I'll call this t capital T. It happens to be the total flight time before this thing hits the ground. And unlike the usual case, now my acceleration in the x direction is not 0. We are accelerating to the left, so it's negative. And in fact, because the force is mg, the acceleration will be g again to the left. So we have a nice equation here. Notice that it'll be easy to solve for capital T in that case. In the y direction, I want to end on the ground. I'm calling the origin of my coordinate system the foot of the cliff. I'm going to start at this height h, and notice that we are, in this case, throwing the projectile directly horizontally, so there is no initial y component of the velocity. And just like in the x direction, in the y direction, the acceleration is also negative g. Two equations, two unknowns. This should be pretty easy. From this first equation, we can see that we have two solutions. It's quadratic, but we can factor out a capital T. One of them is trivial. Yes, I know that x equals 0 when t equals 0. That's the starting condition. I want the other one. So dividing out by t, we can solve for the flight time. It's 2v0 over g. That's the total time that it's in flight. And then we can substitute this in here and solve for v0 in terms of h. So let's do that. All right, doing some cancellations and moving stuff around will give us our speed. And we end up with root gh over 2. Okay, so that is the speed that is required to just barely get the wind to blow this thing right back to the base of the cliff. QED.